We are discussing the software testing strategies today. Now, when you are dealing with softwares and you are following some, say, SDLC or software process, then the most important thing which comes and the most time you should uh, invest is on the testing. So, software testing is again a whole science by itself, because software can be tested in various phases. It can be tested in various ways. There are various methodologies which has been which are prevalent and which has been adopted. So we'll talk about all these in software testing strategies. So software testing is the process of exercising a program with the specific intent of finding errors prior to delivery to the end user. So software testing is done with an intent to find an error. And sometimes people also say that if you have not unfolded or surfaced any error, then you have failed in your testing. The testing means try to uncover as much error as possible. And we are talking about error because this is done before the delivery to the end user. Because after that, in this particular book, the errors after delivery are known as defects. So what exactly testing tells us or represents or shows us? First and foremost is the errors. Testing shows the errors and the requirements performance, whether the requirements are fulfilled or not. The performance, of course, the vital part of most of the software today, and also testing is the indication of quality by itself. There are certain strategic approach for software testing. First, if we want to perform the testing effectively, we should conduct technical reviews, and that too effective technical reviews. We have talked about the formal and informal reviews. By doing these reviews, many errors will be eliminated even before the actual testing could commence. So testing begins at the component level and work or goes or spreads outward toward the integration of the computer based system entirely. And there are various testing techniques that will be appropriate for different software engineering approaches at different points of time. So there is not a set standard which needs to be followed. Okay, this is the testing we have to do. This is the testing. But in all, we'll talk about a formal way, what to do, when to do, how to do. But it may depend on what software engineering you are adopting. The testing is conducted by the developer of the software. For large projects, you can also go for an independent testing group for IV and V, independent verification and validation. And please understand that testing and debugging, they are different activities. But debugging must be accommodated or it must follow any testing strategy. So we were talking about the V&V, that is verification validation. So these are two terms which are often confused in relation to software engineering. First, we'll talk about the smaller definitions. That is, verification means, are we building the product right? That means if you are being told, I always take this example, 2 plus 3 is 5. Now, have you implemented 2 plus 3, 5 correctly? Addition of 2 plus 3 should be 5. It should not be 6. This is verification. And validation is, are we building the right product? That means you have done 2 plus 3, but it may be possible that you have been asked to perform 2 into 3, that is 6. Though you have performed 2 plus 3 equal to 5 correctly, but it may be possible that you are not doing that thing which are exclusively being you should address with respect to the requirements. So the verification refer to the set of tasks that ensure that software correctly implements a specific function. Verification means all the tasks or set of tasks that will ensure that software correctly implement a specific function, or whether the outputs of a certain phase conforms to the input of the previous phase. This is also definition in various books. And validation refers to again different set of tasks. So these are different tasks that ensure that the software that has been built is traceable to the customer requirements. In verification, sometimes people say that it is the basis is your design or design document. But this is also given in some book, that verification is done with respect to the design document, while the validation is done with respect to the customer requirement. Now, who tests the software? Who is responsible? He may be a developer, he may be an independent tester. For a developer, because he understands the system better, and he will test it gently, and is actually driven by the delivery, the time bound or time boxed approach he is going to take. If he is a independent user, first he need to learn the system, and he'll try to break into the system. That means he'll try to find out the loopholes, the problems, the errors, whatever name you may give, because he has to find something which has some problem. And he is actually driven by quality. So an independent tester will be driven by quality, while a developer will be driven by the delivery. So testing strategy, it starts with the unit test. While you are developing the code, or in the code generation activity, you test units. If you have made some functions, or say a module, that may be a group of function. So if you have created a module and you are satisfied that you have done it correctly, then you can subject it to the unit test. Then after this, what you can do is, there are module 1, module 2, number of modules you have made. Now you want to check the interfacing between these modules. So you go for integration testing. So this comes very near to code generation. After code generation, the design modeling. And then after you have seen the interfacing between the modules, then you go for the validation test. Okay, validation test. Then once you have seen the validation test, you have combined them, you have checked them, you go for the system test. And this validation test is with respect to the analysis modeling. Whatever you have found in the models you have made in analysis, the validation test is based on that. Finally, the system test is a system engineering approach. When you combine the system, complete system, it may contain some external entity, it may have some hardware connected to it, you may be connected with the databases, you may have some external files you may be using. All these are tested at once. It's all combined, and you treat the system as a whole, and you perform the system test. So these are the software testing steps we have just seen in the figure. So initially, the test will focus on each component. These are the components, individually, ensuring that the units, they function properly as a single unit. That is why this unit, if it is working fine, we call it as a unit testing. So we test for a single unit. And unit testing will make heavy use of testing technique that will exercise all the path in a component control structure. That is, you are doing some sort of white box testing. We'll talk about this. To ensure complete coverage and maximum error detection in a unit, in a single unit. Then when these components are being checked and verified, then you go for the integration. Okay, components can be assembled these components can be assembled now in the form of components. And these components, they are assembled and they are integrated to form the complete software package. Then the integration testing is done. And this integration testing addresses the issues associated with the dual problem of the verification and program construction, because you must have made a unit or verified the unit properly, but when they are combined, it is necessary to see that once you have combined them, they are working well. And after the software has been integrated, that is, you have constructed, there are a set of high order tests which are to be conducted here. And there are certain validation criteria which we established during the requirement analysis. We need to evaluate that. So validation testing now is the final assurance that software meets all its informational, functional, behavior and performance issue. So you validate for functional as well as non-functional components, means requirements. The software, once it is validated, they are combined with the hardware, the people, the databases, etc. And then the system testing as a whole, all elements, they are meshed properly, and that overall system function performance is achieved or not. So testing strategy, we begin testing in small, that is, we started with the unit, and we move toward the testing in large, that means as a system. There are two ways we can think of in terms of conventional software, like the structural approach, and in terms of object-oriented software. So the conventional software, the module or a component is in actuality our initial focus, and then we integrate them. Then integration of the module will follow. In object-oriented design, the software testing strategy, we focus when testing is small, changes from an individual module to an object-oriented or OOPS class that encompass. So we are treating class as the unit that encompass the attribute, the functions, and implies the collaboration and communication between a number of classes also. So in these strategic issues, Tom, he argued that software testing strategy will succeed when software testers they perform certain implied things, like they specify product requirements in a quantifiable manner long before testing commences. So before testing could commence, they have to actually specify the requirements in certain quantifiable manner and state testing objectives explicitly, that what they are wanting to achieve. Then they should understand the user of the software, and they should develop a profile for each user category and develop a testing plan that will emphasize the rapid cycle testing and build a robust software that is designed to test itself. Means the software should be testable by itself. The effective technical reviews, it will act as a filter prior to the testing. So before testing could be done, the reviews should be done properly. And we conduct technical reviews to assess the test strategy and test cases by themselves, whether the test strategy is okay or test cases they are made properly or not. And then a continuous improvement approach should be adopted for testing process. So in unit testing, we have a software engineer. He needs to test a module. So for that, he needs certain test cases. And on the basis of this test cases, the module will be tested and the results will be shown. In the unit testing, since we have certain test cases, and what we are interested in here is the interface. The module will have interface, the local data structure which are in this module, the boundary conditions, the independent paths in the module, and the error handling paths. So in this unit procedure, we have the testing which may be performed in terms of stubs and driver. So you want to check this module, but this module is being called by some driver, or this module is calling some other modules. So module is being called by some module and module is calling some module. But by the time you are checking this may be possible that the module which is calling it may not be available, or these stubs or the module which calls certain modules, they are not being made. So the module which is calling is called driver, and the module which is being called is called stub. So in unit testing, we will require the driver and the stub for a module to be checked properly. So in unit test procedure, since a component is not a standalone program, component cannot, because it is always related with some or the other. So we need to have driver and stub software. This must be developed for each unit test. So driver is nothing more than the main program that accepts the test case data and passes it on that data to the component which we are interested in, and it will print the relevant results. While the stubs, they serve to replace the modules that are subroutine, that is actually invoked or called by the component which we are testing. So a stub or a dummy subprogram, it uses the subordinate modules interface and maybe may do minimal data manipulation, like print some verification of entry or may return control to the module undergoing testing. So drivers and stubs, they represent the testing overhead in unit testing. That is both the software that must be written, that is formal design is not commonly implied, but that is not delivered with the final software product. So when you are making the driver or stub, this is an overhead. You are not going to actually give it to somebody because you are actually making driver and stub. Then we have certain operation or options for integration test strategy. One is the Big Bang approach. One is your incremental construction strategy. In Big Bang approach, if this is your module 1, module 2, module 3, and say module n. In Big Bang approach, we combine all the module at once, and then we try to test them. This is a Big Bang approach. In the incremental, first we add these two. There is a proper incremental strategy or a plan of integration testing. So you combine them, then you check. Then when these are verified, these two integration, then you add this third one. When this is done, you add this fourth one, and so on and so forth. So we have a top-down approach in integration. For this top-down integration, the integration process is performed in a series of 5 steps. That is the main, this is top-down, so we start with the top. So the main module or control module is used as a test driver, and stubs are submitted for all components directly subordinate to the main control module. Okay. And depending on the integration approach selected, that is, you can go depth first or breadth first. These subordinate stubs are replaced one at a time with actual components. So you start with main, and then you say build M5. Then you add M3. Then you add M4 like this. Depending upon if you have followed the breadth first, then you will go by this approach. Otherwise, if you are following the depth one, you'll add M3, then we will add M5, M7, M7 after M3. Then tests are connected at each component which is integrated. And on completion of each set of tests, another stub is replaced with the real component like this. So regression testing, we'll see about that, may be conducted to ensure that we have not introduced any new errors after some patching or some debugging has been done. In bottom-up integration, a bottom-up integration strategy, what we do here is, there is this is against to the top down we have seen. The low level components, they are combined. These are combined into clusters like this: cluster 1, cluster 2. Sometimes they are called as builds also, that perform a specific software subfunction which is related. And then a driver or a control program for testing is written to coordinate these test cases or test case input and output. Then this cluster is tested. Then drivers are removed and clusters are combined, moving upward into the main program structure. So these are driver added after clusters are being checked. There is another approach, top down or bottom up, they can be combined. This is known as the sandwich testing. So in this sandwich testing, which is an approach where we combine the top down and bottom up together. So in this approach, the usage of stubs, which is the called program, and the drivers, which are the calling program, that are used by the programmers wherever the programs are incomplete. So in this top modules are tested with stubs, or you can have clusters, which is the, you can go from bottom to top. You can make cluster first, you can make the driver first. So these these worker modules are grouped into builds and they are integrated. So regression testing, it is the re-execution of some subset of tests that have already been conducted to ensure that these changes have not propagated unintended side effects. Means you have tested one and you have fixed one error. Now this testing and fixing may not introduce any other error. This is checked by regression testing. So whenever software is corrected, some aspects of the software configuration, that is the program, documentation of the data that support, is changed. So regression testing would help us to ensure that the changes what we have done due to the testing or for some other reason will not introduce unintended behavior or additional errors. So regression testing may be conducted manually also, or by just re-executing the subset of all test cases and using the automated capture of playback tools. Then we come to the smoke testing. Very important, because this is asked in question answers, because it is a typical type of testing. So this is a common approach for creating daily builds for product software, daily builds. So these are the steps. First, the software components that have been translated into code, they are integrated into a build. So you have a build, whatever has been created, they are translated into the code and they are integrated in the build. And this build includes all data files, libraries, reusable modules and engineered components that are required to implement one or more product functions. And then a series of tests is designed to expose the error that will keep the build from properly performing its function. And the intent should be to uncover the showstopper error, the most prominent error that have the highest likelihood of throwing the software project behind schedule. And the build is integrated with other builds, and the entire product in its current form is smoke tested daily. So it is smoke tested or daily build. The integration approach may be top down or bottom up. So what you do, you do a daily build, you add whatever you have made today and you combine them and you do the build daily. And then you try to find out the showstopper that is likely being interested or being impacting the schedule of the software delivery. In this smoke testing, McGraw-Hill, he described the smoke testing in this way. The smoke test should exercise the entire system from end to end, and it does not have to be exhaustive, but it should be capable of exposing the major component. So the smoke test should be thorough enough that if the build passes, you can assume that it is stable enough to be tested more thoroughly. First you test, then you again test. That means once you test and you assume that in the smoke testing it has passed, that the build has passed, now it is stable enough to be testable, so you can test it more thoroughly. Smoke testing provides a number of benefits when it is applied to complex time-critical software projects. First, the integration risk is minimized, the quality of the end product is improved, the error diagnosis and the corrections are simplified, and the progress is easier to assess. Then we come to the object-oriented testing. So it begins by evaluating the correctness and consistency of, first of all, the analysis and design models that you have made in that phase. So testing strategy somewhat changes. Now the concept of unit broadens due to encapsulation. Now you cannot have just a module as an encapsulation. The integration will now focus on classes and their execution across a thread or in the context of usage scenario. How these classes are executing, in what terms, and the validation uses the conventional black box methods in object-oriented testing. So the test case design, they draw conventional methods but will encompass certain special features. In the object-oriented testing strategy, the class testing is the equivalent of unit testing. So class, please understand, in object-oriented, class testing is equivalent to your unit testing. And unit within the class are tested, operations within the class are tested, the state behavior of the class is examined, and then the integration is applied in 3 different strategies. The integration can be thread-based, use-based, and cluster testing. So this thread-based testing, it integrates the set of class required to respond to one input or an event. So say C1, C2, C3, these are the class which are required to respond to one input or an event. So we combine them, we integrate. These are called thread-based testing. Then the use case testing means we combine C1, C2, Cn. These are the set of classes that will respond to one use case. And the clusters testing, this integrates the set of class C1 to Cn that will demonstrate the one collaboration. So use case, collaboration, or the thread-based, these are the integration applied in 3 different strategies. So we are coming to WebApp testing, because WebApp testing is again very important. So the content model for the WebApp is reviewed to uncover errors. You must have some content model that you have made, content model, while you are actually analyzing and modeling in the design phase. And the interface model is reviewed. First content model is reviewed, then the interface model is reviewed to ensure that use cases can be accommodated. And then the design model of the WebApp is reviewed to uncover navigation errors. So content interface design, and then user interface is tested to uncover errors in presentation or navigation mechanism. Then the functionality or functional component is unit tested. So you start with content, then come to interface, then design, then user interface, and then to final functionality, because functionality will be there in WebApp. After this, navigation through the architecture is tested. The WebApp is implemented in a variety of different environmental configurations, and again we need to check or test the compatibility with each configuration. And the security tests, these are conducted because in WebApp security plays a very important role. In an attempt to exploit vulnerabilities in the WebApp or within its environment, or any loophole or a back entry being open, and then the performance tests are conducted, because WebApp performance is very important. The WebApp is tested by the controlled and monitored population of end users, and because WebApp can be used by multiple users. So the result of their interaction with the system, they are evaluated for content and navigation errors, usability concerns, compatibility concerns, and WebApp reliability and performance. Then we come to the validation testing. So in validation testing, software validation is achieved through a series of tests that will demonstrate conformity with the requirements. So we are only interested and much more interested in our requirements. So a test plan outlines the classes of tests to be conducted first of all, and the test procedure defines the specific test cases that are designed to ensure that all functional requirements are satisfied, all behavioral characteristics are achieved, all content is accurate and properly presented, and all performance requirements are attained, document is correct, and the usability and other requirements are being met, like transportability, compatibility, error recoverability, and maintainability. We perform the alpha testing and beta testing. So alpha testing is also known as the looking over the shoulder. So alpha or over the shoulder testing. Alpha testing is conducted at the developer side by the representative group of end user. So you, at your location, the end user will come and now you are going to test. The software is used in a natural setting with the developer. Then we go to the beta testing. Beta testing is conducted at one or more end user sites. So they can be our friendly customers or users. So set of friendly users will be using at their location your software. So unlike alpha testing, the developer generally is not present there. So the beta testing is the live application of the software in an environment that cannot be controlled by the developer by himself. Then in the system testing, that is the final testing which we are talking about, it has various testing involved, like recovery testing. That is, it forces the software to fail in a variety of ways and verifies the recovery is properly performed or not. Security testing, that is the protection mechanism. It will verify the protection mechanism built in a system. In fact, protect it from improper penetration. Stress testing, it will execute a system in a manner that demands resources in abnormal quantity, frequency or volume. So it is about resources which is being required. Sensitivity testing. Or sometimes it is also combined with the sanity testing. So this is a variation of stress testing. In certain situation, most often in the mathematical algorithm, a very small range of data contained within the bounds of any data for a program may cause extreme and even erroneous processing or profound performance degradation. So even a small range will create an extreme degradation in the performance. This is the sensitivity testing. And the performance testing, we test the runtime performance of the software with context of the integrated system. And deployment testing is we test the runtime performance of the software with context to in an integrated system. Then we come to the debugging, that is the diagnostic approach. So debugging will follow the successful training. When a test case will uncover an error, a debugging is a process that will result in the removal of the error. And the debugging process will usually have two outcomes. The cause will be found and corrected, and the cause will not be found. So in the debugging process begins with the execution of test cases. The results are assessed and a lack of correspondence between expected and actual performance is encountered. Then in many cases the non-corresponding data are a symptom of an underlying cause as yet hidden. And the debugging process attempts to match symptom with cause, thereby leading to error correction. So in test cases, we have debugging here. Test cases, the results are given to debugging. They are suspected causes and we add the additional test. The identified causes, they are corrected and the regression testing is to be forwarded. There are certain consequences of the bug. There are various categories of bug. They can be function related bugs, system related bugs, data bugs, coding bugs, design bugs, documentation bugs, standard violations. So the bugs can be mild, they can be annoying, disturbing, serious, extreme, catastrophic and infectious. So now this is catastrophic. There are certain stage and that will cause, it depends on how much it is causing your business and the life actually. The money and the life. There are certain debugging techniques, brute force, backtracking, induction, deduction. So how to correct the error? So there are certain questions which need to be asked if you want to correct the error. Is the cause of the bug reproduced in another part of the program? In many situations, this program defect is caused by a certain erroneous pattern of logic that may be reproduced elsewhere. What next bug might be introduced by fix I am about to make? That is regression topic we are taking. So before the correction is made, the source code or better the design should be evaluated to assess the coupling of logic and data structure. And what could we have done to prevent this bug in the first place? So this question is the first step towards establishing any statistical software quality assurance approach. So if you correct the process as well as the product, the bug will be removed from the current program and may be eliminated from all future programs. So we have certain final thoughts. Think before you act to correct. Use tools to gain insight, like you have JUnit, you have LDRA. There are so many open source options available to test your software in various terms. You can do the static analysis, you can do the dynamic analysis, and if you are at an impasse, get help from someone else. Once you correct the bug, use regression testing to uncover any side effect. So this was the testing strategies, and we'll be talking about testing more. Thank you so much.